Folks, welcome back. This is the video for section 10.2, the unit circle, part 2. So this, we're going to start off with the unit circle. There's a couple different reasons why I included this example problem. Number one is we need to have some repetition with the unit circle so that that thing's committed to memory. Number two, I wanted to show you the unit circle in a slightly different format. In our previous unit circles, basically these two unit circles would be right on top of each other. But in this one, the unit circle on the left shows multiples of 45 degrees. And I want to show you how you can think of the unit circle as split into fourths. Okay, so that right there represents pi radians. So if we have that split into fourths, we can say that this is pi over 4. This is pi over 2 because that's 2/4, also known as 1/2. 1, 2, this is 3/4 or 3 pi over 4. And this is 4/4, which is also known as pi. So if I keep counting by fourths, let's see, 1, 2, 3, 4. This one must be 5 pi over 4. This one is 6 pi over 4, which we would reduce to 3 pi over 2. And let's see, 7. So 1, 2, 3, 4, 5, 6, 7 pi over 4, all the way to 8 pi over 4, which is 2 pi. Remember, we started at 0, we ended 2 pi, which is the same value. Okay, so what I want you to do now is I want you to pause the video and I want you to write in the x and y coordinate for each of those angles. Folks, hopefully your unit circle filled in looks like mine. You should notice that the majority of these values involve root 2 over 2. We just have to keep track of the plus or minus signs. Everything in quadrant 1 is positive. In quadrant 2, our x values are negative, but y is positive. Here's a typo. In quadrant 3, they're both negative, so that should be a negative x value and a negative y value. And then in quadrant 4, x is positive, but y is negative. All right, let's move on. Now I'd like to look at this unit circle on the right. This one, the top half of the unit circle is split into sixths. So each of those dots represents 1/6 of pi. So we have pi over 6, 2 pi over 6, which is really pi over 3, 3 pi over 6, which is really pi over 2, and you'll notice that this one appears in both unit circles, the one that we've split into fourths and the one we've split into sixths. So 1, 2, 3, this one's 4 pi over 6, which can be reduced to 2 pi over 3. If you'd like to count in thirds, you could count that as 1/3 and that is 2/3. So to see how those thirds can be viewed on the unit circle. All right, so continuing around here, we now have 5 pi over 6, 6 pi over 6, which is also pi. And now, so I'm increasing to values greater than 1 pi, so this is 7 pi over 6, 8 pi over 6, which is also known as 4 pi over 3, 9 pi over 6, which is known as 3 pi over 2, and again, that value is repeated in the unit circle that's split into fourths. I'm going to count here just to make sure I don't lose track. So I start here at 0 pi and I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pi over 6, which is also known as 5 pi over 3, 11 pi over 6, and then back to 2 pi. Remember, 2 pi and 0 are the same. So what I want you to do now is I want you to pause the video. I want you to fill in all the x and y coordinates for these points and then check your work. Okay, folks, check your work there. Hopefully you have the same x and y coordinates that I do for the unit circle split into multiples of 30 degrees or pi over 6. Okay, let's scroll down and look at example 2 here. It says, given the information below, determine all possible values for the angle theta. So the first example we have here says that the sine of theta equals 1. Remember that the sine of theta is equivalent to the y-coordinate on the unit circle. So if I go back up and look at my unit circle, I find, let's see where we have a y-coordinate equal to 0. Excuse me, a y-coordinate equal to 1. This guy right here works. So pi over 2 must be theta. And if you answer theta equals pi over 2, you would be wrong, because we did not determine all possible values for the angle theta. Pi over 2 is what is referred to as the primary angle. But remember we talked in our last lesson about coterminal angles. So I need to add revolutions of 2 pi times k. Okay, so this value plus 2 pi k represents multiple revolutions, either in the positive direction or the negative direction. So the correct answer for this problem is theta equals pi over 2 plus 2 pi k. Complete answer. Okay, so now let's look at the next example. We have cosine theta equals root 2 over 2. Remember, cosine is our x-coordinate for points on the unit circle. So let's take a look back up there and see where we have an x-coordinate of root 2 over 2. It looks like that occurs here at pi over 4, but it also occurs down here at 7 pi over 4. So I think I'm going to have two different answers. I think I'm going to say that theta equals pi over 4 is my primary angle, plus 2 pi k. Those are my coterminal values. Or theta equals 7 pi over 4 plus 2 pi k. So this one has two answers. Folks, I'm going to go ahead and pause the video here. I want you to do the same. I want you to go through and work through the rest of the answers in this example problem, and then check your work with what I have. Okay, folks, here you'll see the answers for parts C through G. Take a look at a couple unique things here that I want you to notice. Go ahead and pause the video to check your answers, but a couple things I want to highlight here. Notice in this one that I gave you a number that wasn't written in simplest radical form there for the cosine ratio. So to convert that to something that we see on the unit circle, we would multiply by root 2 over 2. Gives us this negative root 2 over 2 in simplest radical form, and that corresponds to 3 pi over 4 or 5 pi over 4 on the unit circle. Moving on, this one, part E, is we're talking about the sine theta equals 0. So when does the y-coordinate equal 0? Well, that happens at 0. It also happens at pi. So we have 0 plus 2 pi k or pi plus 2 pi k. We can simplify that and consolidate it as a single statement, pi k. Oftentimes these ratios repeat every half circle, so that we can write those as plus pi k. In this case, it's 0 plus pi k, which we can just write as pi k. The same isn't true in part F. The cosine, or the x-coordinate, is only -1 at pi, so we have to add 2 pi k. So these two examples look similar but slightly different. You can check part G on your own now, but I want to talk about part H. Part H is kind of interesting, and I believe it's going to stump some students. The answer to this is there is no solution. There's no solution because the cosine ratio must be greater than or equal to -1, less than or equal to +1, and if you take pi and divide it by 2, you get something greater than 1. So remember, this has to be true. which leads us into our discussion about the domain and range of trig functions, which we're going to slide down and talk about here in number 3. Okay, so the domain of sine and cosine, all real numbers. You've seen the graph of the sine function before and the cosine function, and they are continuous on the real number line. So you can input any value you want, any real number value, into the sine and cosine functions, and you're going to get an output. Another way to think of that is, remember, on a unit circle, we can continue to rotate in the positive direction or the negative directions as much as we want and still find a x-coordinate and y-coordinate for a point on the unit circle. Therefore, the domain is unrestricted for both of these functions. Now, how about the range? Well, I just alluded to it. The range for each of these functions is from -1 to +1, including the endpoints, so we're going to put square brackets. Tangent, though, is a little different. Hopefully you remember our friend tangent from right triangle trig. The tangent of theta is equal to the sine of theta divided by the cosine of theta. So the first thing we'll do is we'll talk about domain. We do have a domain restriction here because we do not want to divide by 0, so the cosine of theta cannot equal 0. Well, the cosine of theta equals 0 anytime theta equals pi over 2 or 3 pi over 2. So that's an example of where we're going to look at pi over 2 plus 1/2 a revolution around the circle, or pi radians, either in the positive or negative direction, and we have to take those values out of our domain. So domain of tan theta is pi over 2. Theta cannot equal pi over 2 plus pi k. However, the range of tangent is unrestricted. And I'm going to let you prove that to yourself by looking at a graph of tan theta on your calculator. Okay, folks, we are at the 12-minute mark here, so I'm going to go ahead and shut this video down, and you will see the rest of this lesson in another video.